Okay, good afternoon, everyone. In already the fourth session of this event on EV charging best practices and power quality. Glad to see you here again. We will have a two-day event where this day we'll be focusing on best practices of EV charging, and tomorrow will be more of a deep dive on power quality research from different universities all around the world. You can still register for those sessions as well from our website, and afterwards you can see all the sessions on our YouTube channel. So feel free to keep an eye on that as well. Thijs and I will be monitoring the questions during the presentation, so you can ask them using the questions box in the GoToWebinar menu, and afterwards we will have time to ask these questions to the presenter. And if there are many questions, we will forward the questions by email to him, so he can answer them by himself. Something else to mention is that this webinar is made possible by the Progressors project, which is working on future electricity EV charging infrastructure to have more efficient and more renewable EV charging infrastructure. This presentation will be from Evangelos Kotsakis. He is from the Joint Research Center in Ispra, Italy. He holds a bachelor degree in computer science and a Master of Science and PhD degree in electrical and electronics engineering from the University of Salford, England. Since 2004 already, it's quite a long time. He's working for the Joint Research Center as scientific officer, and his research is focusing on smart grid technology, system technology, system interoperability, and ICT vulnerabilities studies. And this presentation will be about EV idle time estimation on charging infrastructure, comparing supervised machine learning with regressions based on a paper of his group from recently. So looking forward to this presentation. I will make you a presenter now, and you can start sharing your screen.
Hello, everybody. My name is Kotsakis Evangelos. I'm working for the Joint Research Center of the European Commission. I'm going to give you a presentation on EV idle time estimation. The presentation has actually two parts. One is dealing with the use of supervised machine learning for identifying key variables affecting the idle time. And the second part is the use of neural networks for forecasting the idle time. Forecasting, I mean next day events. JRC, in fact, is the Joint Research Center of the European Commission, is the technical branch of the Commission. We do research in several fields. I'm involved in energy and climate unit department, directorate. So my department has two labs. One is in Petten, Netherlands, and the other one in Ispra. The lab I'm responsible is in Ispra. The lab in Petten focus more on smart appliances, home automation, and smart devices that could be installed in houses. The lab in Ispra is dealing more with simulations. We do a lot of work on hardware in the loop. We have also a lot of charging stations we test in our lab from different providers. We also have a battery energy storage system that we use for managing energy, for implementing flexibility scenarios and all these kind of things. So my presentation, I'll start with the first part, which is actually how to use supervised machine learning to identify key variables that affect the idle time. I'll explain a bit the motivation. We go then to see some data analysis we did before actually the analysis is kind of cleaning, for instance. A few words about the accuracy and the metrics. I'm going to present the main variables that affect the idle time and some analysis we did with partial dependencies based on the variables that we identified, and some conclusions. So first of all, idle time is a very important factor that actually can minimize the overall cost of an infrastructure. For instance, if you have a total idle time in your infrastructure very high, then probably you don't use your infrastructure as expected, so you lose profit. And then probably use also some new users. And in order to incorporate new users, you have to oversize your infrastructure. So this comes with a cost. And idle time is something that should be considered when someone deploys a charging station in a country or an area. So of course, idle time is not always bad. Okay, it looks bad at the beginning, but it could be used as an opportunity for flexibility. I'm gonna say a few more words on this. So also identifying the variables that affect the idle time is very important to in order for a company to give incentives to the users, knowing the main variables that affect the idle time. So all in all, identifying the main factors that affect idle time is very critical. It's very critical from many points of view, from the economy, from the use of the network, from the investments that someone has to make in order to have a better coverage and better services to the users. So we use, to do this analysis, we use some a data set from ELAD. Actually, the coverage of this data set is from January 2012 to June 2018. We have more or less 1,700 public charging stations, most of them with 1 or 2 connectors. This at that time represent the 60% of the charges in the Netherlands. So in our data set, we have 1.8 million transactions, and we have more or less 82,000 EV drivers. So the data we have in this data set are mainly transaction ID, the charge point ID, the time of start, of the transaction start, the time of the transaction stop, meter starts, meter stop, the car data, idle time, the total energy used transferred from the charging station to the EV, the maximum power provided by the charging station, and of course some georeference data. We have the latitude and longitude of the charging station. The charge time, idle time, and max power are calculated based on the meter readings and also the transaction. The segment, the road segment, has been added by us in order to be able to classify better the charging stations. Before actually we did the analysis, we performed some kind of cleaning of the data. We identified that there are some transactions that didn't make any sense. For instance, transactions with no transfer of energy and connection time over 200 hours. So this kind of transactions are considered outliers, so don't bring any information to the analysis, so have been actually left out. So the data set after the cleaning of the data, we came up with 733,000 observations that corresponds to 63,000 EV users. So of course we did some scaling just to have a more precise reference to the data. So a kind of normalization was applied before actually we did the analysis. So the main variables that actually affects the most the idle time is charge time, idle that have been considered in this analysis are charge time, idle time, total energy, and max power. Here in this table we see actually the range of these variables. For instance, charging time comes from half an hour to 5.5 hours. Idle time from a few seconds to 8 hours. Total energy from 0.1 kilowatt hours to 76 kilowatt hours. However, we see more or less that 70% of the data set has 3.4 hours charging time, and the idle time of this 75% of the sample is 4.5 hours. So this is actually a little analysis we did to understand better where we are, what is the ranges of these variables, and the algorithms we applied three different algorithms for this analysis. The first one is a extreme gradient boosting algorithm, random forest, and gradient boosting. Okay, extreme gradient boosting is actually an effective implementation of the stochastic gradient boosting. The gradient boosting is a machine learning algorithm used mainly for classification or regression predictive modeling problems. The random forest is a machine-learning algorithm that builds multi-decision trees and merge them together to get a more accurate and stable prediction. So if we see how the performance of these three algorithms, for instance, the first one is the performance of the random forest. The second one, B, is the gradient boosting, and the C is the extreme gradient boosting. Here you see the variables that affect the most the idle time using these three different algorithms. And in this table down, there is actually the accuracy of this algorithms. So for random forest, we have an accuracy of 50–60%. Gradient boosting 59%. Extreme boosting is 60%. Okay, one can say, okay, even the extreme boosting, which gives a better performance, 60% accuracy, okay, doesn't say a lot. However, for this analysis, it is sufficient because it can, all of these algorithms can give us the most important variables that affect the idle time. And if you see the three algorithms are a bit consistent, okay, maybe they have different scores, but at the end they catch the main thing. And even and the main thing here is to identify the most important variables that affect the idle time. And as we see, for instance, we choose at the end extreme gradient boosting because it provides better performance. So we see that the variables that affect the most the idle time is the day hours, max power, total energy, and charge time. So in this figure here, we can see what we call a partial dependency. For instance, we took 4 of these 10 variables. We took charge time, day hours, max power, and total energy. And we fixed 3 of them, and we changed the 4th one, and we see how this 4th one, the changes of the 4th one, affects the idle time. For example, on this figure, on the first upper left figure, we see how charge time affects the idle time, keeping the other 3 variables, daytime, max power, and total energy, constant. So we see, for instance, in this figure that the charge time, or when the charge time is small, the idle time is small. Okay, it makes sense. If the charge time is small, it means that the connection time is small. So the idle time, the expected idle time is small as well. So you see that this, as the charge time increase, the chances to have longer idle time increase as well. To some extent, for instance, after 3.5 hours of charge time, we don't have an increase, a dramatic increase, let's say, of the idle time, which means that to some extent the system is stable after charging time is when the charging time is longer than 3.5 hours. And the idle time is almost 2.5 hours. So the day hours here we see the day hours is in seconds. So 0 is midnight, 440,000 is midday. So you see that when actually we are close to the night, to midnight, we have longer idle times. When actually we go closer to midday, we have less idle time. This makes sense because during the night people sleeping, they let the car charging in the charging station, so it gets full, and then we have an idle time. It's still connected in the morning. So the max power, the other figure here, we have the max power, shows that when the max power is very small, the max power is the maximum power of the provided by the charging station. So when the max power is small, the expected idle time is small. This means that it takes more time for the EV to be fully charged. So the chances to have idle time is small. As the maximum power is larger, then probably we have the EV is fully charged very quickly, faster at least, and then the rest of the connection time is idle time. So the idle time increases as the max power increases. Of course, this reaches a stable point from 4.5 kilowatt. You don't see much difference in idle time. And the last one is the total energy. And this shows how the total energy affects the idle time. We see that when the total energy is very small, the idle time is big. The explanation we can give to this is that when the total energy transferred from the charging station to the EV is small, this is probably because the EV, the batteries of the EV are fully charged. So the next connection time is idle time. As the total energy, which is actually the energy transferred from the charging station to the EV, becomes larger, it means that probably the batteries are flat and needs more time actually to get the battery full, and then most of the connection time is charging time, and the idle time is very small. Okay, so conclusions. I mean, if we want to implement a public policy around these variables, we can use several things. I mean, restricting, for instance, the EV from charging points in certain hours. I mean, it's up to the provider to give some incentives to the users, or notify the users when actually are close to have an idle time situation. Maybe charging extra the user that actually have the EV with long idle times. But in fact, knowing the variables that affect the idle time also could be seen as an opportunity. Opportunity, especially for aggregators, in order to provide some kind of flexibility through ancillary services. So as I said before, idle time is not always bad. Idle time means that the EV is fully charged, so you have energy in the cars. So the aggregator can use this energy and this power from the EVs to implement some ancillary services, manage better the congestion, implement some low scheduling policies, or even perform some voltage control. So all in all is if someone wants to restrict the idle time and minimize the idle time, can implement some policies related to accessing the charging point. However, if you the provider can be flexible enough and use this idle time as an opportunity to provide flexibility services. So I move now to the second part of my presentation. Until now, we have seen I've presented the variables that affects the idle time. Now I'm going to present how it's possible to forecast some events, charging events for the next 24 hours. So to do this, we do a user profiling and explain what we mean with user profiling. Actually, it's a classification of the users. I'm giving I explained a bit the neural network structure, how we did it, and I present also some forecasting results. Motivations. Okay, the main motivation for forecasting is better planning. If I know which charges is going to be used for the next 4 hours and for how long, I can make a better planning. For forecasting charging events is very important if I want to use my network and my infrastructure in the best possible way. To do this, we do first a user profiling based on historical data, and we implement this by using the neural networks. So this is actually the user profiling classifications. We have three different classifications. One is the overnight near home, this ONH. This is the second classification. The second class is the short charging near home, and this is all the other cases. So what do we mean by overnight near home? By overnight, we mean that the charger is used constantly or mostly by this user during night. By during night, here we mean that actually 3 o'clock at the night should be included, and the charging duration should be greater than 4 hours. All the other cases that actually fall in this category, but are not are less than 4 hours, are considered short chargings. So this is the second category, the second class, and all the others, all the other cases are the green class, which is the short charging, other short chargings. So for each user, we take all the charge events, and we use actually, if we consider that we have n events related to a particular user, we use the n-1 events for training the network, and the last event is the event that we try to predict. So we use actually our analysis using the historical data up to n-1 and try to predict the last event. And then we do a little analysis to see how successful was the prediction. So for each user, actually, we identify all the charging events that falls under these three categories. Overnight, 3 a.m. is included, and duration greater than 4 hours. This is the same, but less than 4 hours. And this is all the other events. So for each event, we put all these events in different classes. So this is an exploratory analysis we did at the beginning, just to understand what we can do. So the number of users for which we are able to forecast is 74. Why is this? Because we cannot forecast everything. The success cannot be, for this particular data set, more than 74, because sometimes the last event is a new event for the user. Probably the user uses a new charging station that has never used before, so the system in that case cannot predict this. We can actually predict an event that has been occurred somewhere in the history. If this has not been included in the history, we cannot forecast it. So okay, this is a little percentage of wrong classification after the analysis we did, which is 4 point something. So this is actually let's say a set representation of this class. The overnight near home includes the short connection near home. This is all the other cases, and these are actually are the points that cannot be predicted. So for every user, we try to forecast the next charging event, as I said. So by next charging event, we mean charging time, connection time, and the charger ID, in fact. So the data we provide is the last charger ID, the last connection time, the class of the user, and the user ID. So we, in the first place, we try to determine if the next charging event would be overnight near home or short connection near home. Actually, we classify, we try to identify, to predict, let's say, in which class this event will be. And then we use 3 different neural networks to come with some precise data, with some precise, let's say, prediction. I mean, to predict the charging time, the connection time, all of this. So we have 3, in fact, neural networks for this purpose. So this is actually the first one. We use the last event time connection, the type of day, if it is a working day or weekend, and the type of the next day, the day actually we want to predict, if it is a working day or a weekday. We do this because we identify that this makes a lot of difference. The behavior of the people change from the working days to weekends. So in this particular neural network, we identify the output is whether it's overnight or not. So the next one, in the next one, we have again the same data, time, connection, start, type of day, week, day or weekend, type of day of the next day, and we have actually, we predict the connected time and the charge time. Actually, the idle time is the connected time minus the charge time. So what we need is these 2 variables. And the third one, which is actually all the other cases, is the time that the connection starts, the type of the day the connection starts, and then as an output we have the connected type and the charging, the connected time and the charge time. Okay, this is the mathematical model we use to model the neural networks. Going into details. If everybody wants more details on this, we have also a nice report on this. We can share it with you if you want. Okay, more or less, we have 3 layers in the neural networks: the input layer, output layer, and the hidden layer, which are always connected to all inputs and outputs. Okay, during the training of this neural network, we try to identify the weights. Okay, as long as we have the weights, then we can use the neural network for prediction. Okay. Okay, this is a little more information about the neural networks. So, okay, I'll jump directly to the results to see how the prediction is done. This is actually the x-axis is the score of the forecast, the forecasting. So the y-axis is the percent of the forecasting. The x-axis is the error in hours. So we see that for the half an hour, we have a forecasting of 55% success. For the second one, for instance, for the second half of the hour, we have oops, sorry.
Okay, thank you for your nice presentation.
Sorry, I exceeded the time.
No problem. We still have some time for questions, so about 10 minutes left for questions, so that's fine. So the first one is from Jan Roseli, and he's wondering if did you see any differences between the seasons, like the summer-winter difference? Will this impact the idle times or not?
No, in fact, we haven't considered seasons. We didn't actually take into consideration different seasons. We play a lot with different hours, but not seasons. But it's probably a good point for further research, because for sure different seasons can actually modify a bit the situation. Let's say, I mean, the behavior of the people is different in summer and different in winters. Yes. For sure. Yeah, this is a good point.
The cars will have higher usage in the winter. The energy consumption will increase, so maybe you will have less idle times. So that will maybe influence the results as well.
Yes, you're right. Probably there is a way actually to explore this this part, because the needs also in winter is different. Full behavior is different. I mean, the charging itself could be present different patterns in winter, for sure.
Yes, indeed. Yeah. Okay, thank you. Another question is from Shamista about the Shaira. She asks if what's actually happening during the idle time. Is the EV still taking some amount of power, or is it really disconnected from the grid? Is it like putting a device in standby mode? How is it? How does it work? Do you know about this?
Can you please repeat, because I didn't actually understand the question. I mean, there was some interruption in the.
Yes. So how will the EV work when it is in idle time? Will the EV still be consuming some power, or will it be absolute zero?
I'm not sure that I understand the question. How the idle time is affected by? I don't understand the question. Can you please repeat?
So the question is, I will rephrase it. So during idle time, the EV charger is still taking a small amount of power, right? Or is it
no, it's that doesn't take any power, any energy from there. When actually the EV is fully charged and then still connected, but doesn't get any energy, any power from the charging station, is zero. I mean, the energy transferred during the idle time is zero.
Okay, yeah, that's good to know.
Of course, there are some consumption, if you mean, in the charging station. The charging station, in order to operate, consumes some energy. Okay, this is another part. But I'm talking about the energy transferred by the from the charging station to EV. During idle time, this is zero. But okay, consumption exists because in order to have the charging station operational, you consume a little energy, of course.
Yeah, so just electronics in the station itself will consume something, that the car will just be disconnected at that point. That's clear. Another question, because I think the research you did focused mainly on the public chargers. Do you think there will be differences when you look to home chargers people have at their home wall boxes? Will there be a difference in the idle time or the flexibility you have over there?
You mean for the home chargers?
Yes.
But this is not a concern, because home chargers, I mean, you are the only, you mean the portable ones you have at home? not the public ones.
Mm-hmm.
But their idle time doesn't make any sense because you are the only user of the charger. So you can use it you can decide to use it or not to use it. The problem starts when you use some publicly available chargers. And then from the moment you have an idle time, you are somehow connected to the charger, and this excludes some other users from using the charger. So it's actually you waste valuable resources from the network. But at home, you don't have this problem. You have your own charger. You are the only user. Nobody else can use it anyway. So
Mm-hmm.
there's sense to talk about idle time in home chargers.
Yes, and regarding flexibility, if you would say that instead of idle time, you would have the possibility to use bidirectional charging instead of during the idle time, how will this affect the results? Do you think?
Yeah, okay. Flexibility, implementing flexibility from using the car energy at home is another story. Doesn't concern more the charger, but rather the provider that provides energy to your home. So of course the aggregator has, the aggregator has a say at this point, but this issue is not linked to the charger. You can apply flexibility at home even without the charger. That's my point.
Mm-hmm.
But when you have a public infrastructure for with thousands, millions of charging stations, then the charging station is actually the entry point of applying flexibility. Whereas at home, you may have other entry points. You don't need to actually to do everything through a charger.
Mm-hmm. Okay, that's clear. Thank you for your question, for your answer.
Okay.
Another question is from Arthur Andruskiewicz. I hope I pronounced it correctly. Can your forecast system adapt quickly to the fast evolution of the EV market in the Netherlands? Because the data you used will be from 2018 or earlier. How will it change if you compare with this
the quality of the voice? Sorry, the quality of the voice is very bad, and I hardly understand what you say. Can you please repeat?
Yes. So there's a question regarding the data you used. This is from 2018 or earlier. But in the meantime, a lot of new EVs were adopted in the Netherlands. So how will this change the situation regarding the results?
Okay, we have got the new data set from ELAD, and we managed to see how different is the situation with the new data set in comparison with the old one. For sure, if you have more charging stations, more transactions, you may have more accurate analysis. And it is important also to see how this changes over time, and how the new installations of the charging stations can improve the situation by minimizing probably the idle time.
Okay, this was the final question. Again, thank you very much for your presentation and the discussion. The next presentation will be in 15 minutes from Thijs from ELAD.nl about the best practices from the test lab we have over here. So I hope to see you over there. And yeah, for now I will close the session.
Okay, thank you very much.
Bye bye.
Bye bye. Huh?